Greetings and welcome to another edition of CASS Talks. I'm Rafael Brum, professor at UFRGS Brazil and vice president of the IEEE CASS Rio Grande do Sul chapter. I'll be your host in today's CASS Talks. If you missed on any of the previous talks, please check our videos in this channel. We have now more than 170 talks for you to be watched at any time you would like. Before we invite our guests, let us first take a look in the upcoming events that will take place here and elsewhere in the cloud. You've seen Iberchip 2022 among the next events, and I would like to announce that for those who wishes to be part of Iberchip, we are pleased to offer a free IEEE plus CASS membership for all authors of accepted papers. So don't miss this opportunity to share your work with everyone at Iberchip 2022. So without further ado, let me welcome Professor Fernanda Castensmith, head of the Applied CS department at UFRGS, who will chair today's session. So welcome, Fernanda. Thank you for being with us today.
Thank you very much, Rafael Brum. It's a pleasure to be here. And today I'm here to introduce my colleague, Professor José Rodrigo Azambuja. Then we are going to have the pleasure to see his talk. The title is In Network Computing and Switch Virtualization Walk into a Bar. Very interesting. I'm joking. Yes, so José Rodrigo Azambuja holds a bachelor degree in computer engineer from the Federal University of Rio Grande do Sul, a master degree in computer science, also from the same university, and a PhD in computer science from UFRGS, and electrical engineer in CAET, like a co-tutela double diploma. He is currently as an associate professor at UFRGS, chair in the IEEE CASS Rio Grande do Sul chapter, president of Porto Alegre's Council for Science, Technology and Innovation, and IEEE senior member. José Rodrigo has authored over 50 publications in journals and conferences, and the book Hybrid Fault Tolerance Techniques to Detect Transient Faults in Embedded Processor. He has experience in the area of computer science with emphasis on synthesis architecture, working mainly on the following topics: network accelerators, embedded systems, and fault tolerance. We are very happy to watch your talk today. Thank you very much.
So thank you, Fernanda. Thank you, Rafael, for opening the session. I did not mention here, but Fernanda was my advisor, so it's a pleasure to have her introducing my talk here at CASS Talks. And so, as you can see, my talk starts with a joke, like in network computing and switch virtualization walk into a bar. So what happens next, right? So I've been working on the IEEE CASS talks for a long time right now. I believe I gave a few talks in person a few years ago, and Rafael and I, and also Ricardo, we've been managing these CASS talks for the past 2 years. So I'm actually really glad to be here giving this talk finally in this virtual environment. And so let's go to the talk then. Let me just switch here very quickly. Okay. So in-network computing and switch virtualization walk into a bar. So this is one of those cases where I'm not sure if you know those YouTubers and streamers which try to blend stuff. Like they have a blender and they throw an iPhone inside and turn on the blender and check it. Well, will it blend or not? So this talk is kind of on the same idea. So we have two major concepts here, which are in-network computing, and a second, which is switch virtualization. So what happens when we mix these two together? So this is actually an open question on the research topic. So we actually don't know what we can do with these two things. So the idea of this talk is to introduce you with some background on networking, on the main concepts which must be taken into account to understand in-network computing and virtualization, switch virtualization. So as we are talking about circuits and systems, this is actually a very interesting area, but still most of our talks are more related to microelectronics. So I'm having a nice background on networking. So if you don't know anything about computer networks and so on, don't worry, I have a nice background here. So for the outline of this presentation, I have a background on networking. So I'm going to explain briefly what computer networking was back in the day, and the day would be around the 60s, so around 60 years ago. Then I'm going over programmable virtual switches, or PVS. PVS is our proposed platform for doing lots of stuff. And then through the end of the presentation, I'm going to give you some applications on how to use in-network computing, actually with switch virtualization, for artificial intelligence, and also for CDN, which stands for Content Delivery Network. So we are talking about how Netflix delivers content over networks, or how you can see a soccer match, or how you can play on xCloud or on Stadia. So all these applications are inside CDN. And finally, I'm going to end this presentation with some collaboration opportunities on what we have to offer um, in part of this collaboration, and what can a student look forward to working with us. So first of all, our team. I have a large team. I believe most of them are here in the audience and they are watching the video right now. So I have Weverton and Luciano. They are both professors at the Federal University of Rio Grande do Sul, so they are my colleagues. And they are mostly from the networking side. And then we have Matheus Sacchetti. Matheus Sacchetti is the principal investigator of most of this talk. So Matheus is our hardware guy. So Matheus is the guy who programmed and described most of the hardware lines that we are going to see here. And then we have Guilherme. Guilherme finished his master's a few months ago, and Guilherme is more on the programming side. And then we have some undergrad students. We have Pablo, Ivan, and Leonardo. So Pablo is currently working on an internship at an FPGA company here in Porto Alegre, Rio Grande do Sul. And Ivan is finishing his computer sciences course, and Leonardo is close to finishing his engineering degree in computer engineering. So let's move on to the background on networking. So starting our talk. By the way, this talk is supposed to be around 40 minutes, 45 minutes, something like that. So I hope I won't bother you guys. So starting on this background, networking started back in the 60s. So packet switching started back in the 60s, and then in the 70s we had the birth of TCP/IP. So I am sure most of you know what TCP/IP is a protocol for addressing computers in the web and making connections. And then we had the internet. So the internet changed a lot from the 60s and 70s to what we have today. In the 80s and 90s, we actually delivered the World Wide Web, which stands for the triple W, so www.something from your website. And in those days, changing the whole World Wide Web was kind of an easy thing because you only had a couple computers and a couple connections and a couple links. So if you wanted to change all the routers of the internet, you would change about, I don't know, I'm guessing 100, 1,000 routers, and you have a new internet, right? So only a couple hundred devices, and there you go. You have a new internet. So today we have something else. I mean, most of you guys have seen some not so nice cables, some on the backbone of internet. Some of you might have heard the noise that these guys make. And basically, we have a completely interconnected society, technologies. We have cloud providers. We have, let's say, cell phones. We have IoT. So currently, the state of the network, the computer networks that we have, is something completely out of our control. So can you just imagine how many routers we would have to replace just to add a new protocol? Let's say the IP protocol. We are currently mostly using IPv4, and IPv6 um, has been they are actually trying to deploy IPv6 for, I would say, at least a decade. And I am sure that some of you guys have routers that do not support IPv6. So updating the network, modifying the network, it's something completely out of our league. So basically, we cannot. It's really hard to upgrade stuff on the internet, and one could say it's virtually impossible to completely upgrade the internet. And this is what the network people call networking ossification. So you cannot change stuff. It's really, really hard to upgrade stuff. And you have a very challenging area to improve networking. Okay. So let's take AT&T, or in Brazil, let's take Claro Net, for example, or your provider. Convincing them to change part of their network infrastructure is almost impossible because you don't want to change something that is working already. And if something goes wrong, well, internet falls down. And I know, I know that you will probably be very pissed if your internet goes down. So it's a hard thing to do, and it has been for since the beginning of the internet, since the beginning of networking in the 60s. But there is some hope. For example, this scenario has been changing recently, but I mean recently, I mean like in the past decade, not much more than that, with three new concepts. So I'm going to go over these three concepts, and this is basically the background on networking, okay? But are some very specific concepts. So the first one is called software-defined networking, or SDN. The second one is network virtualization, and the third one is domain-specific language. And the fun fact is that domain-specific languages is not a new thing. It's actually a very old thing. The new thing is domain-specific languages applied to the networking domain. So anyway, let's start with the first one, software-defined networking, or SDN. So what's the idea behind software-defined networking? The idea here is, if you imagine a router does have a firmware, so it has a huge network stack or protocol stack, and then this whole firmware works on top of a hardware. And the hardware is usually a chip, an ASIC chip that basically forwards packets. So the idea here is to decouple these two things. So if you check digital circuit design, you usually have the control path and the data path. Let's imagine a microprocessor here. You have the data path, where you're basically moving data from registers to memory, from registers to register, memory to memory, and so on, IOs to IO, or something like that. You're basically moving data from point to point. This is basically the data path of a microprocessor. And then you have the control path. And the control path decides what happens. So should a branch take place or in the control flow of an application or not, right? So where do we start running this kernel or this kernel application? How do we call a function? So this is on the control side. So previously on computer networking, we only had one thing. You have a router and that's it. Okay, like some sort of a single cycle microprocessor, something like that, something very old. So the idea behind software-defined networking is decoupling the control plane from the forwarding plane. So the forwarding plane now receives packets in its inputs, decides, process these packets and outputs these packets to be transmitted somewhere, right? So it's very straightforward, some sort of a pipeline where data comes in and data comes out. So what happens to the data or the branches or the control flow of the data processing is on the control plane, right? So, this is kind of an old concept when we talk about microprocessors and systems architectures, but it is quite a new concept for networking. So decoupling networking from the control from the data or the forwarding plane. So in the end, what you have here is the intelligence on the control plane, and what I am going to show you soon about the match and action tables, right? So how these things works. So let me give you an example of how this works. Let's say we have a control plane and a forwarding plane. Here, it's the same figure as before, and these guys are running some a stack of protocols. So we have Ethernet, we have VLAN, so virtual local area networks, and we have the IP version 4. And now what you actually want to do is you want to add a new protocol to the stack. So 10 years ago, you would take your router, I don't know, donate it somewhere or just throw it away and buy a new router that has MTAG. This is what you would do like 10 years ago. And imagine doing this for the whole internet. It's just unfeasible. So now what we do is we reprogram the control plane, and the control plane tells the forwarding plane, well, now you actually know MTAG, and now you're going to process MTAG. So what happens is we can just add the new protocol to the forwarding plane, and this whole guy is updated, and now it's working. Okay. Of course, you do need some hardware structures here to implement some protocols. Okay. For example, let's say floating point. If for some reason your protocol requires floating point, it would be at least smart to have some floating point units in your forwarding plane, right? But anyway, you do have some margin here to add and remove protocols. So now we have a new router or a new switch or something like this that runs MTAG. But now I want to update IPv4. So, but you can check here. I'm not actually replacing IPv4 with IPv6. I'm actually wanting to add my own protocol, which I'm calling here IPv6. It can be here 7, 8, 9, whatever. It doesn't have to be called IP. You can call it whatever you want. The idea here is that we want to replace a non protocol by a customized protocol that you have just invented. You could remove some parts of the header. You can change how the headers work. Anyway, you can change whatever you want in this protocol, and you want to update it. So through SDN, this is feasible. Basically, what we do is we reprogram how the switches see and process these packets. So I'm telling, okay, forwarding plane. From now on, instead of looking at these bytes of, let's say, a packet is an array of bytes, and I'm saying instead of looking from bytes 0 to 7, you're going to look from bytes 3 to, I don't know, 10, for example. And with this information, you're going to decide to, let's say, drop this packet or forward somewhere, right? Or change some bytes and so on. So we can do that through SDN. And by reprogramming how the switch is seen process the packets, we can remove IPv4 and add the new IPv6. And then, simply like that, you have an updated router. Okay. And here we have a full picture, a complete picture of how SDNs work. Let me just go previously really fast. So as you can see here, we have the control plane and the forwarding plane. I'm actually making things simpler, okay? But in reality, what we have is something like this. So as you can see here, in the bottom part, let me see if I can, yep, okay. So in the bottom part here, we have the data plane or the forwarding plane. And as you can see here, we have some network elements. So we can have multiple network elements. And then in this part here, we have the control plane. And finally, which I had not shown you before, we have the app plane here. So, sorry for my mouse here. Anyway, so what happens is the tenant or you, for example, you have an application and an SDN application, and basically what you do, you go through an interface and a control interface, and this interfaces connects to the forwarding element, and it reprograms or changes the network element and so on. And of course, throughout this whole thing, you have a management and an admin communications here. So this looks nice. I mean, it's not a nice picture, but anyway, the idea here is nice, and but there are some challenges here, especially in terms of security, in terms of access, in terms of knowing which network elements you have, in terms of knowing what kind of control you can do over your network elements and so on. But anyway, this is an overview of SDN and what it provides, right? So moving on, we have network virtualization. So I have a second example here of network virtualization. And as you can see here, from the bottom up, right? What we have here in the bottom is an infrastructure provider. So what you have here is cables and the backbone. Okay, you have routers and switches, and you have actually physically your interconnected network. So you have some submarine cables going from South America to North America, from South America to Europe, and so on. This is actually those links, these physical links here. And you have some guys that are actually forwarding these packets. But as you can see, having the physical layer and actually having the logical layer are two different things, because usually you have a company or a country or an organization that has the physical layers, and you rent this structure to ISPs. So this would be some internet service providers, such as I do believe that AT&T, for example, has both of them. Okay, but that's not always the case. And then you have a virtual network. So you can make your own interconnections virtually on top of this physical layer, right? And then you can have a virtual child network on top of your parent virtual network. I mean, this is missing a U here, virtual network, and so on. So this is the idea of virtualization. You add abstraction layers to your physical infrastructure so that you can more easily deal with your network. So just to make sure here, we have on the bottom part, a physical router. So this guy may host one or more virtual routers. So this is one for N relationship. So we have one physical router which can deal with multiple virtual routers. And this is usually built upon ASIC chips, on network processors, and on FPGAs, but mostly on ASIC chips, because we need very, very low latencies. So we are talking about nanosecond latencies here. So these guys really need to act really fast and forward packets really fast. Not only that, but you also need some throughput. So it's not only the how fast the packet travels on the network, but how many packets you can travel at the same time throughout the network. And then we have here a physical link. So as you can see here, we have actually some cables, some fibers, and so on. And this can be implemented with any sort of technology. So going back to our picture, when we look at the virtual side here, the virtual side, we have a virtual link, which is a logically isolated from virtual link. So you have to logically isolate the physical channel. So you have some access credentials here to actually use the physical layer. So we have a whole abstraction layer on top of the physical layer. And finally, we have some virtual routers. So a virtual router can actually be run on top of a GPP, a general purpose processor. It's not going to be fast. It's going to be really, really, really slow because you have to run code, deal with IOs. This can be really complicated. It can run on top of a FPGA, for example, or on top of a router, an ASIC router. And of course, these guys have to be isolated from other virtual routers. Okay, they are interconnected, but still they are isolated. Each virtual router has its own resources, but these physical resources might be shared with other virtual routers. Okay, we can look at a virtual router as a virtual machine, like a VM. Okay, so you have your own random access memory, your own RAM memory, and your own space, disk space, but the physical disk is being shared with other VMs, and the same for the RAM memory. So basically, this is what we have on network virtualization. This is also something new. And then for the third background part of our talk, we have domain-specific languages. So DSL. As I said before, domain-specific languages are not something new. They are actually quite old. But when applied to the networking domain, they become something new. So the idea here is that a DSL is a computer language specialized to a particular application domain. So you can have DSLs for analog systems, for digital systems. We have plenty of them for networking, for, let's say, CUDA, for example, on the GPU side is kind of a specialized language, right? Because we are dealing with massive amounts of data and among lots and lots of other options. But the interesting thing here about the networking domain is that the first language to deal with the networking domain is from 2015. So it's a 6-year-old language. If you think about the C language dates back to the 70s. So we have C language for 50 years. That's almost 10 times more than we have networking domain languages such as P4. And I mean, C is not even the first language. You have a few other languages previous to C. And I'm not sure, but I would say they date back to the 50s and the 60s. So and the first appearance for a domain-specific language for networking domain is on 2015. So this is actually amazing. As you can see, this is why we have a so ossified network, because the technology that is going to change that is being developed in the past decade. That is really crazy. The first language, as far as I know, that started competing with P4 is POF, which stands for Protocol Oblivious Forwarding, from 2017. So that's 4 years ago. And still last year, we had a new language, which is one of the first languages that takes into account the hardware substrate, which is called Lyra. So Lyra is 1 year old, I would say 1 year in a couple months. So as you can see, this is quite a new research area. Well, anyway, from these languages, I am going to focus on the P4 language, okay, because this is the most known, most open source, it has a huge community and so on. So when we talk about P4 again, this dates back to 2015, so that's 6 years, 6 years ago. It is maintained by the P4 Language Consortium, and this consortium is backed up by the Open Networking Foundation, if I'm not mistaken. And it is open source, and it is permissively licensed code, so anyone can use P4. P4 it's currently in its version 16. If I'm not mistaken, this is because of the year of P4, version 16. And yeah, so I am not actually going to give you examples on the P4 language because I think this would be wasting your time. You can just go and download some examples online. But I'm going to discuss briefly how P4 works. Okay. So the idea of P4 is to act on top of this switch architecture, which is called PISA, so Protocol Independent Switch Architecture. So as you can see here, protocols come this, packets come this way. So you have here a network packet, and it goes out this way, right? So as you can see here, we have some sort of a pipeline, and on each stage, something happens to the packet. So we have on the input a parser. So the parser tries to parse what's happening on the packet. So it kind of opens the packet and parses some of the headers and some. Anyway, you can actually program that, right? So it basically opens the packet and checks stuff, right? And then you have some these stages here, which are actually called match and action stages. So here we have 3. You can have multiple of these guys, like 10, 16, whatever. And then you have a deparser. So what happens here, you repacket your packet, your network packet, and you send it away. Okay. So the main idea here is we open something, a string of bytes. We open it, we decipher what's happening on it. So we parse its data, and then we process its data throughout the pipeline. So here, and then we put it back together and we send it away. Okay. So this is basically what the PISA switch architecture says one should do. And this is what actually P4 does. So P4 describes the parser, the deparser, and what happens in the middle. Okay. So if we look at the middle, okay, so let's check this guy here. So what we have here is a very regular structure. So we have memories and ALUs, so arithmetic logic units and memory. Okay. Currently, P4 does not support floating points, so we are talking about integers here. So what we have here is bunch of memory and ALU. And I'm sure Fernanda, the chair, who can see some resemblance with an FPGA here. So a lookup table. And this is basically what happens here. The memory kind of acts like a lookup table, and the ALU performs some sort of data processing. So this memory plus ALU, they are something like a match and action table. So you receive a data, you check it against the memory, and then you decide to do something. That is pretty much the same thing as a lookup table on an FPGA design. Then, of course, you have some integers processing here in the middle, and basically you describe how that works. Okay, so this is basically P4 and a small spice of PISA here. So to finish our background, I swear to you guys, I'm almost finishing the background. We can talk about some current products that work on top of this whole thing. So as you can see here, we have Intel Tofino, and you might see some issues here because we have Intel Tofino, and then we have Barefoot Tofino here. So the thing is, Intel bought Barefoot, and of course bought it because of Tofino. So what Tofino does is, you can see here one of those hack units, network hack units, so like a 1U or something like that. And as you can see here, we have a Tofino ASIC and an Intel CPU. And then you have I/O ports here, right? So packets are coming here and they are leaving also from this side. Packets come into this ASIC, and the CPU is controlling this ASIC. So the ASIC returns stuff. So basically what we have here is a forwarding engine, which is this Barefoot Tofino ASIC, and the control engine is on top of the CPU. And as you can see here, the idea of Tofino is the same as Pisa. You have a parser, and then you have, it's not shown here, but you have a deparser here on the outside. And then you have packets coming in, packets coming out. You have some buffering, and you have some retransmission here. So you can actually output a packet back into the pipeline. So let's say if you want to process the same packet in the pipeline a few times, you can actually do that. And on the control plane, we have the Intel CPU here. Tofino is currently in its second version. Okay, it actually can achieve a few terabit of data. So it's actually a nice thing. It's a nice technology, a nice product. It's just not very easy to buy one of these because these are still in development. And on the FPGA side, we have Xilinx SDNet plus the NetFPGA project. So for the NetFPGA project, a few universities and companies formed an organization to maintain this NetFPGA project. So the idea of the NetFPGA is to run P4 code on an FPGA. Okay, so this is the basic architecture. These are some input ports, so data comes this way, and then you have basically a multiplexer here, multiplexes all the data coming in, and then you have this guy. So this guy is actually your switch. I'm sorry for my bad mouth handwriting. You have your switch. This guy can be a custom switch, so whatever you program in P4, theoretically you can deploy in this guy, and then you have packets going out. Okay, and then you have the control here. This control is being done by a microblaze because we are talking about Xilinx, and it has some AXI interconnects and so on and so on. So the idea here is we have a P4 code, and then we send this P4 code through the Xilinx SDNet, okay? And the idea behind SDNet is a high-level synthesis tool apply to P4. So instead of inputting C code and synthesizing it to HDL, you're actually inputting P4 code and synthesizing it to what we call simple SUMI switch. SUMI is the name of the NetFPGA, so NetFPGA SUMI. And then you take this bit stream and you input inside this architecture. And as you can see here, we have a parser, a deparser, and match and action pipeline. So the idea behind PISA is still the same here. Okay, so this is another product. Again, I'm not sure you can buy Xilinx SDNet. I believe it's still in development. We have some early access to it in its first version. I believe it's in its second version right now. It's really hard to get access to it. So what's missing, right? By the way, I finished my background, so probably now you know everything you need to know about networking together our proposal. But also I showed you Intel Barefoot. It works really nice. Xilinx SDNet. I mean, you probably won't be able to buy this stuff because they are still developing it. But the point is, what's there to do, right? So, what's missing? Number one, network slicing is missing. Network slicing, and let me go back a few slides. As you can see here, we have a single switch we can put here. Going back to Tofino, we have a single switch that we can put here. A single switch. You cannot put two switches on the same place. Okay. Actually, to be fair, Tofino 2.0 has 4 of these chips, so you can put one switch on each chip. So, but still, not ideal. So what's missing is we use the same hardware resources to deploy multiple switches. So let's say 2, 3, 4 switches. And why? Because of multi-tenancy. So the idea here is like an Amazon Web Services. So instead of renting your server, you're actually renting your router. So you have a group of resources, and you can have 4 or 5 clients deploying each client its own router on your hardware. Okay, So for example, let's talk Google Stadia. Stadia is the gaming platform from Google where you can play on the cloud and so on. So the idea there is that Google can do that because it has its own network infrastructure. So its network is really fast. You can send packets really fast. So the idea here is the same. Okay. So you can rent your own network, your own physical infrastructure, even though if it's a virtual switch, it's your switch. Okay. So this is the idea behind network slice and multi-tenancy. Then we have profiling and debugging. This is quite straightforward. You want to profile or debug your protocol, your deployment, or wherever. And finally, switch migration. So the idea behind switch migration is that you actually can have an app store for protocols. So you sort of buy or you rent your own switch, and then you can buy a bunch of protocols from an app store. And if you want, you can just switch or you can just migrate your switch from one point to the other one. Okay, so it's kind of like you have in your own VM and switching computer. Okay, currently none of this is possible. None of these are possible. So this is our main focus here. So programmable virtual switches or PVS. So we argue in favor of a virtualization model that can offer you the ability to preserve your IP. So your stack of protocols is your own. You can make your own protocol and deploy it without having to share its source code. Um, Still, you need to have bare metal performance because we are still on the networking domain and you want to switch packets as fast as possible. And you need to have control access security. So this is what we are tackling with programmable virtual switches. So this is the idea behind programmable virtual switches. Number one, you have two tenants, tenant one, tenant two. The one on the left is the blue tenant and the green tenant on the right. So the idea here, each tenant has its own applications, and then you have to go through a control plane to access the data plane. Okay, and so a couple of these figures are not completely correct because PVS is actually the whole system. Okay, but we are focusing here on the forwarding engine of PVS. So what we have here is the same hardware, the same board, let's say the same FPGA board with two different switches, one from each tenant. Okay, and PVS can manage all of this. PVS can run the forwarding elements, PVS can deal with the control plane, and PVS provides access to different tenants. On a general scale, again, this is kind of what PVS looks like. So again, here is the forwarding plane. So if we can focus here, packets are coming in, packets are coming out. And here we have a whole implementation of a switch, which is based on the P4 language. And this is tenant 1 virtual switch, we have tenant 2 virtual switch, and we have multiple other switches for multiple other tenants. And of course, this brings out some real challenges here. For example, how to secure tenant access, how to guarantee that one switch won't blow up the second switch, how to maintain resources allocated for different switches, and so on. So we have a couple of challenges here that I'm going to show you how we work on them. So we have the control engine abstraction. This is the guy responsible for access control, and we have the forwarding engine slicing that is responsible for distributing resources among different switches, virtual switches. So what I'm going to show you about programmable virtual switches, or PVS, is the forwarding engine slicing. Then I'm going over the control engine abstraction, like very briefly, and then two sorts of implementations, FPGA implementation and Asic implementation. So for the first one, forwarding engine slicing. So the idea here is to have multiple virtual switches in the same substrate. We also want HLS support, so high-level synthesis support, so that you can, you can actually write your own hardware and deploy it inside inside PVS. But again, this is very counterproductive, right? You can just use high-level synthesis and P4 and better describe your switch. And then we need to have full and partial FPGA reconfiguration because we need to add and remove switches. We have to, for example, let's say one tenant is off, it actually rented for, let's say, an hour your switch. So at some point you have to remove his virtual switch and you have to add a second virtual switch. Or let's say you still have some space on the board and you want to add a third or a fourth virtual switch. So you need full and partial FPGA reconfiguration to do that. And finally, a public open source implementation. And let me tell you, our work is based on the canonical NetFPGA design reference, which is a picture that I showed previously on the SDNet plus NetFPGA. And this work is from 2019. So as you can see, 2 years ago only. So again, for the PVS, we are going to initially focus on the forwarding plane. So it's this guy here. So what we are going to do is we are going to expand it. Oh, thinking again, this is the same picture. I'm just going to zoom in here and show you what happens inside of the forwarding engine. So I'm not considering the CDPI agent or the control. We do have a control interface, but I'm going to focus on the rest. So let me zoom in this picture, and this is what we have. So again, packets are coming in, packets are coming out, right? So the main difference is this VS array. So VS stands for Virtual Switch Array, okay? So the idea here, the main difference actually against the canonical design reference from SDNet plus NetFPGA is that instead of having a single switch, we have lots of switches, okay? So as you can see here, we have tenant 1, tenant 2, and then we have some sort of a space. So we have some predefined resource area where someone can just come and deploy its own virtual switch. So it's a very simple, straightforward modification, like it's a copy paste, right? You take a switch, copy it, and you paste it a few times. But the problem is, with this, we have lots and lots of challenges. For example, let's say a packet comes into, it is multiplexed into this IVSI, and the question is, what happens with this packet? I mean, previously we had only one switch, so you just forward it to the switch. But right now we have a few of them. Not only that, we have a few switches and we can have more, or we can remove switches. So number one, we have to check if this is a valid packet. If we are going to send it to a valid virtual switch, if the virtual switch is actually deployed, or if we have to deploy the virtual switch previously to sending this packet, and a lot of other problems that we have to deal with. But anyway, we do this through the IVSI. So this guy multiplexes all inputs, checks it against its ingress table, and just sends it to the correct virtual switch. Virtual switch then does what virtual switch do, and sends it to the output. So here we have some buffers, some output buffers. We still have to do some checkings, and finally we send the packet away. So this is the main idea of the forwarding engine. The idea is pretty simple, but to implement this is another thing. Also, we have a control interface. So this control interface deals with these ingress tables, with the egress tables, and also deals with each and every virtual switch. And then we have here some control access issues because you need to have your, you have to guarantee that the right tenant is accessing its own switch. So we have lots and lots of small issues here that we have to deal with before actually deploying this guy. So on the next step, we actually have to implement a virtual switch. So to do this, we also use the SDNet plus NetFPGA basic design flow. And this guy is divided in 3 steps: the white step, blue step, and yellow step. So on the first step, what we have is a switch.p4. Okay, so you have your description of your switch in P4. You have the descriptions of the registers you're going to use and of the tables you're going to use. So what we do here, we input these guys. So they are here. They go through Zarlink's P4 compiler and through Zarlink's SDNet compiler. And then we create a few files. So switch that goes here, switch cli goes here, and the switch HDL goes here. Okay. So on the second step, we have the wrapping of the switch HDL. So what happens here, switch HDL is generated through SDNet, and this is an encrypted HDL. So what we do is we take this encrypted HDL, we wrap it around a wrapper, which includes AXI buses, so AXI light, AXI stream. We add some information to this wrapper to know, well, this switch actually has an ID, and then we generate this final VS HDL. And this final VS HDL is the guy that you can deploy on your FPGA. And then for the third step, this is on the driver side. So what we have here, I don't have actually a picture, but what we actually need are the board drivers. We need the reconfiguration drivers, and we need some memory maps, and finally some drivers to access your switch. So this stands for CLI, or command line interface. So every switch in the board will have its own command line interface, and we have to interface all of these things with the control engine abstraction. So on the control engine abstraction, I'm going to be very brief here. So let me just show you here an example. We have a flow starting on age 1 and going, so it's inputs here, outputs here, or here. Okay. So what we do here is on the age 1, as you can see, it starts and remains stable. So age 1 is okay. This is kind of connecting an oscilloscope to age 1, age 2, and age 3. So age 1 is sending packets, and age 2 is receiving packets. And as you can see here, age 3 is not receiving anything until a point where we reconfigure this guy, and suddenly age 2 drops because that age 1 flow is not going to age 2 anymore. It is now going to age 3. So this is just to show you that it actually works. I have here, I'm just going to go over this. I think my time is. So what we have here is I'm showing here a poisoning attack from an application, which is actually trying to destroy a second application. And this usually happens when we have inside communication. So in the same board, the switches are communicating, and one switch can actually break the other one. So this is mainly Ivan's work. It's his graduation project, and he implemented a great system here that stops this. Now let's go for implementations. So FPGA implementation. So we are implementing this at the NetFPGA SUMI board. This is the most recent NetFPGA board. We're running at 200 megahertz. As you can see here, we have 4 optical interfaces connected here, 1, 2, 3, and 4. So each of these is a 10 gigabit per second port. So we have up to 40 gigabit per second. And so we deployed PVS in this guy. We have a full reconfiguration option and a partial reconfiguration option. The problem with full reconfiguration is that we have to completely stop everything to do it. On the partial, we can do online partial reconfiguration, so the system keeps working. The problem is that with full reconfiguration, we have the whole board, so we can actually deploy, I would say, around 8 virtual switches with full reconfiguration. And on partial reconfiguration, we have some issues deploying 4. So you can see here, 1 instance, 2 instances, this is another VS, and this is another VS. So this was actually done by Pablo. So Pablo, I know you're there, so thank you. And some resource usages. So I'm comparing here P4 net FPGA. So this is for a single switch, and this is our option. So as you can see here, we use 11% of the board against 10% of the board. So it's a small increase in order to be able to allow multi-tenancy, virtual switch virtualization, and so on. And we have some application switches here. As you can see, they go from 6% board occupation up to 16. So usually our bottleneck is memory. If the switch uses too much memory, this is usually a problem for us. So some experiments here, we have port saturation. So in red, you have here PVS, and then you have in green net FPGA, and the loopback is basically a cable, no switch, is a direct link. So as you can see here, it's kind of okay. And by the end, we have some TCP congestion here, and these results are kind of slightly awkward, but they all go back to, they all saturate at the same point, more specifically at 9.5 gigabit. So you have to pay attention that we are comparing to a single wire, and the single wire is at 9.5 gigabits. So we are actually saturating at the same time. I mean, there is no degradation here. Then we are checking board saturation. So as I said, we have 4 10 gigabit ports, so it saturates at 40 gigabit. And as you can see here, PVS is in purple, and in green we have the canonical reference. So for an input of close to 40 gigabits, okay, this is injected packets. So injecting lots of packets. This is this experiment uses a loopback packet. So the packet stays inside the router forever. So for 10 packets, we can measure latency and throughput in this experiment. So we are here at not sure exactly here. And the P4 net FPGA is slightly better than us, but I mean by a small margin here. In terms of latency, we have the green line and we have the red line. So latency is about something like 3 nanoseconds. So the correct data is throughput drops by 6.5%. This is not good. This is not bad. And this is also our first version of PVS. Now newer versions have improved this data, and 1.8 nanosecond difference here from these guys. I believe this is on average. So and then simulated performance. So this is simulating packets. This is for net FPGA. We have some better data already. Again, for the first version. We have for the level 2 switch 120 gigabits maximum. For PVS, 20% below that. So this is a huge drop. 20% is just too much. But still, here we have 3 virtual switches running in parallel on the same board, and we have 115 gigabits. So anyway, there are some data to be improved, but still this is good results. Especially because PVS can handle multiple virtual switches and NetFPGA has a single switch. And also I have here a comparison, I guess, P4 Visor. This is, let's say, an early implementation of P4 to high-level synthesis to HDL. And as you can see here, both NetFPGA and PVS are like 20 times faster than this guy, 25 times faster than this guy. Anyway, so we have a proof of concept, active port and board saturation, which is 9. We have bare metal performance, more or less 10%. Simulation shows we could reach 100 gigabit, which is nice. We have full and partial reconfiguration. So we kind of achieved most of what we wanted to achieve. However, we are still far away from terabit capabilities. So terabit is far, far away from us still. So this Virtex 7 board can only achieve around 100 gigabits. So we would need at least 10 of these boards to achieve terabit. So this is just unfeasible. Newer boards can maybe achieve 200 gigabit per second, 250, but still far away from terabit. A terabit would be 1,000 gigabit, right? So this comes for our next part, which is Asic implementation. So on the Asic implementation, the idea here is to improve performance. So we want to reach the terabit per second and maintain programmability. So we still want to reprogram fully or partially switches. So we are aiming for a 65 nanometer technology running at 1 gigahertz. We had some criticism saying that we cannot reach 65 nanometers at 1 gigahertz. We actually can. And for the FPGA fabric, we are considering an Vertex Ultra Scale, which is the 13P here. This is not the newest board, but is one of the largest boards. And for this work, I have to thank Samuel from Taltech in Tallinn, Estonia. He actually performed one of the first CASS talks early in 2020. So you can go check in the channel how to build a trustworthy billion transistor chip. And he is our silicon guy. So he's the one who makes usually the tape outs and so on for us. So this is what we have. Really quickly, we have here FPGA logic. So this is supposed to be FPGA fabric. So you can still reprogram switches. And then we have all the buffering and the multiplexing, demultiplexing, buffering, so on ASIC. So this is from here to here. This is all ASIC logic, right? And then we have the actual physical layer. This is more analog stuff from here. Okay, so this is our idea is to fix the architectural side and keep reprogrammability for the FPGA side, so for the virtual switches. So what we had here is in terms of square millimeters, we had a total of 47 square millimeters for this guy. Number of cells, 71,000. Dynamic power total, 28 watts. So guys, first of all, this is a lot. Okay, this is a lot of wattage. But when we compare this dynamic power to Tofino, for example, Tofino is over 60. So it's still half of what Tofino does. And some results from the synthesis. So we achieve up to 132 gigabits for each switch here. And then what we have is 3200 gigabit PHYs, so 32 ports of 100 gigabits. We have 33 AXI streams. We can deploy from 11 to 26 virtual switches. I'm sorry, one second. So on the FPGA fabric, that adds up to 3.45 terabit per second. And the board itself can achieve up to 3.2 terabit. So we can actually surpass 100 gigabit per second, and we can achieve 3.2 terabit per second with bare metal performance. So this is really, really, really interesting. However, we still have stuff to do. What happens is we still have some space left on the board. So what we can do with this, because we use mainly memory. So on the FPGA side, we use lots of DRAMs and memory elements, but still on the logic side, we still have some space left. So what can we do with this space left? So the answer is offloading applications to run within the network devices. So we call it in-network computing. So finally, we can close our title, which says what happens when in-network computing meets switch virtualization. So the answer is, number one, distributed artificial neural networks and the CDNs. So I'm moving to the end of my talk. This is going to be very brief. So idea number one, artificial neural networks assisted network infrastructure. So the idea here is that we have an artificial neural network and we can actually deploy its neurons inside the switches. And to do so, we can actually process data going through the network. So you can actually collect data on one side of the network and have the answer to that process data in the end of the network. You don't have to actually offload data to a server, process neural networks, and then return this data to the user. You can actually do everything inside the network. So we actually have a prototype of this. So we have SmartNIC is a network interface card. So this guy can generate traffic and can process some stuff. So we deployed one neuron on a processor, a second neuron on a second processor, which is the SmartNIC, and we deployed two neurons on the FPGA. And so we are running here a 1-to-1 network. Not only that, we actually deployed a 1-3-1 network as well. We can see here, I do have some data. So our application here is mainly for in-band telemetry. So the idea is to check how, what's the health of your connections and so on. And for that, you need to get some data. And we have lots of data here. So we have some throughput in packets per second for small packets, for large packets. We have latency for different sizes of packets. We have a comparison against the in-network telemetry. And finally, the maximum distance for network available flows. So this project is actually called Skynet towards smart data planes. And this is a partnership between Brazil, Colombia, and Australia. We have lots of universities here. This is funded by FAPESP, and we are currently working on this project. And finally, for my last example, we have content delivery networks. So the idea here, for example, right now, I am here, somewhere here, right? And we are making a connection to a server where I'm sending my face and my presentation to this original server. And this original server is sending to people in Europe, to people in North America, back to people in South America. And these local servers are sending you this video stream. So this is how things work here. So what happens when one of you actually have an unstable connection to the edge server? So first of all, we are talking about live streaming. So you do not have time to go back, right? We are talking about live streaming. We are talking about Microsoft xCloud. We are talking about Google Stadia. We are talking about someone watching the Olympics or whatever. You just cannot go back and rewatch it. So what happens when your network drops a little bit? So this is the main idea, is to use in-network computing to improve these protocol connections for CDN. So this is actually a partnership between, at least right now, between Federal University of Rio Grande do Sul and the Federal University of Pelotas. So to finish my presentation, I have some collaboration opportunities for researchers. So what we offer complete HLS tools. So you can just give us your P4 and we can turn it into HDL. We have support for programmable virtual switches. We have a couple FPGA boards. We have plenty of SmartNICs for generating traffic, and we also have technical support through our students. So if you do have an application that you want to somehow compute data while data is trafficking through the network, you can just call us and we can prototype it in a week, maybe. That depends on Saket's time, on Mateo Saket. If Saket has time, then it's a week. If he doesn't, maybe a month. And finally, some collaboration opportunities for students. So we are always looking for undergrad, sorry, I'm missing a R here. For undergrad scholarships. So it's mainly students from computer and engineering courses, but we are open to anyone. And we also have consistent master's and PhD positions. So we have options through PG Micro and through PPGC. So you can either work on the hardware side, on the software side, on the security side. And here are our open calls for PG Micro and also for PPGC. So if you're interested, please let me know. And finally, some pictures. This is some of the guys. So this is, of course, me. This is Professor Weverton. This is Mateus. and this is Guilherme here. As you can see, it's dark outside because this was a Saturday night. I think it was around 2 o'clock in the morning, and we are doing some experiments here. You can see switches and people generating traffic, and the FPGA is in this guy here. No, sorry, is it in this guy? I think so. I think the FPGA is in this guy. We have to trace back all the cables. But anyway, and finally, this is a picture of Mateus at SIGCOM 2019. We received the third prize in the undergrad while he was still an undergrad prize. So this was 2019, still in person. Again, guys, these pictures are from 2019. So I do not have more updated pictures because of COVID. And I actually haven't seen Saket Mateus for at least 2 years. So thank you so much. This ends my presentation. So thank you so much. And let me check, Fernanda, let me add you to the stream. So that's it. And I'm sorry if I passed a bit of
No, that's okay. Yes, it was a wonderful presentation. Yes, a very interesting work, very interesting subject, and brings a lot of new ideas, out a lot of ideas for startups, and yes, very interesting. Really. We have one question so far here in the comments from Bruno Borges. Do you have a tool suggestion that simulates this learning journey for network virtualization? I understand that there may be more than one for each part that you presented.
Yes, so I'm going to answer this question backwards. So first of all, yes, there is more than one for each part. And let me give you an interesting joke that we have inside our lab. I am mostly on the hardware side. Waverton is mostly on the network side, so on the software side. And we actually met because we shared the same room in the university. So we said, let's work with something. Let's do something together. We can do something. And the networking guys, they don't care about hardware. They say, yeah, I have this software. I don't care. Let's see if it works. And the hardware guys say, of course, it's not going to work. It's going to be too slow or something like that. So this partnership of this work works because Waverton is a excellent specialist guy on the networking side, and I am on the hardware side. So answering your question, there is more than one part. Yes, definitely. You need to understand the hardware side. You need to understand the software side. And we joke around that Waverton is like the architect, and Mateus and I, we are the civil engineers, like the construction engineers. So he comes and says, so I want a pyramid made out of glass, which is sunny, but it stays cool inside with a basement for this and that. And then Mateus and I, we have to construct this thing. And it's always really hard. We usually spend a few months discussing on what to implement and how to implement before we actually can do something. So, so yes, Bruno, there is more. There is a lot here. We have plenty of subjects, and the good thing, which is also the bad thing, is that everything is very recent. So this is some recent research. So for example, switch virtualization, as far as we know, PVS is the only thing in the literature that can actually virtualize things without replicating. You know, like, besides putting two FPGAs, one on the side of the other. I mean, sharing resources, PVS is the only thing that can actually virtualize switches. And there isn't still a control abstraction that can deal with everything. So even us, we are in the early steps of actually making a product that is fully virtualized. So, so to learn that, I would suggest start by learning P4. This is the starting point. SDNet is kind of hard, so I would ask you to contact Mateus. Send me an email. I can send it to Mateus. Mateus can explain it to you briefly. And the rest, we are still to find out what we have to do. So, for example, how to share a custom resource between two virtual switches. We still don't know how to do that. So I'm sorry if it's not a complete answer, but the answer is complicated.
We have another question. It's from Miriam Lesser. She said that you said about having the tool from P4 to high-level synthesis, yes, code. So I thought it was provided by Xilinx with SDNet. How does your tool differ or add to Xilinx provided?
Yes, that is correct. Our whole project is strongly based on the NetFPGA project, and SDNet is kind of part of it. So let me just go back. I don't think I can go back. But anyway, let me go this way, Fernando, because I'm not going back on my slides. Yes, we do use SDNet, but the thing is that SDNet is purely a compiler from PX to generating a few files. We have a whole scripting stuff that wraps around SDNet. So we use SDNet. We cannot do absolutely anything without SDNet in terms of AGLS. You can actually write your own drivers. You can actually write your own switch and deploy in our platform. But again, this is too costly. So we do use SDNet. We encourage SDNet. If you actually want to write your own SDNet, you can. We did not, so we are using SDNet because it's fast. And so, how does your tool differ or add to that Xilinx provides? So, our tool differs for the scripting around SDNet. So SDNet generates a command line interface, but we have like 10, 12, 26 command line interfaces, and we have to deal with these guys. SDNet sees the global memory of the FPGA as a single memory. As we have multiple virtual switches, each virtual switch has its own memory space. So we have to change again the scripting and implement around SDNet so that we can use SDNet to create what we have. And on top of the canonical, I mean, this is out of the scope of your question, but again, against NetFPGA, they can only do a single virtual switch. So we have to again change basically all the scripting, everything around it. We change most of it, the HDLs. I think the diff from our open source is something around 2,000 to 3,000 lines of code for the first version. So yeah, we have lots of stuff around it, but using SDNet is what makes sense here.
I have one question, José Rodrigo, about the verification process, because of course it's probably very complicated because you have standard flows, companies that provide the flows. You can do your flow, and you have in one point like some constraints that the network already needs, and all the communication protocols and so on, and you needed to make these modifications. You are going to do partial reconfiguration, but you all the time needed to verify if everything it's okay. Yes.
Yeah. So this is a huge problem. Initially, let me show back my slides here. 1 second. So initially, this was our setup here. So this is actually each computer is generating traffic. All this traffic is going to this switch, and this switch has an optical connection to the FPGA board. So this is how we used to add up to 10 gigabits. So this is not ideal. Okay. Now we have these smart NICs, and these smart NICs, they generate traffic as you want. So it is not that simple, but they generate traffic and they parse traffic back. So they measure throughput, they measure latency. You can even add your own custom packets. Let's say, so I'm sending this packet and this packet, like a list of packets. They do that. It's just that sometimes it's hard to get to line rate. So generating 100 gigabit of data is not always that easy. And also, we have some statistics here, because you cannot simply measure and say, yeah, I got 10. No, you have to do this experiment over and over again and find statistical results for this data. So yeah, it's not that easy. It was much harder 2 years ago. Now it's kind of easier, but still not that easy. And we currently have 2 FPGA boards, so we can connect FPGA boards. We can even generate traffic from one FPGA to the other one. So yeah, our setup is improving, but there are still some challenges to perform some measurements. Usually, at least a week, we spend a whole week, like 12 hours a day, performing experiments for writing a paper or something like that.
No, that's nice. No, but I was expecting that. That's very nice. I don't know if you have more questions from speakers.
Oh, I can see here a hello from Estonia from
Yeah,
Samuel.
yeah, Samuel did.
Yeah, Samuel helped us a lot with the Asic implementation. He
No, he
basically
made
did everything.
a huge improvement, yes, in the throughput.
Yeah, because we had like virtualization, but when we compare to the Tofino, for example, these guys are doing like 6 terabit. So if we could have reprogrammability and multiple switches and still get terabit communication, then this would be really, really good. So Samuel helped us a lot there. Yeah.
Okay, so I'd like to thank you again, Jose Rodrigo. I think it was a wonderful talk. Yes, a lot of information, and you are doing a great work. And everybody that is interested can contact you by your email, yes, and your website, as you can put it.
Yeah, my email is here on the presentation. So if you have any questions or any suggestions, collaborations, anything, you can just send an email. If I don't know the answer, I'll just forward it to someone who knows the answer, but I'll definitely answer you. So yeah, so thank you, Fernanda. And well, I guess I'll see you next week.
Yes.
Okay then. Bye-bye.
Bye-bye.